Sven Lidin, you are the chairman of the Nobel Committee in Chemistry that just have awarded 3 Nobel laureates who have developed a new super resolution microscope. Can you tell us what super resolution is? How big or how small is it?
Well, the super resolution refers to Abbe's limit, which states that a microscope can never be give a better resolution than half the wavelength of the light used. And the methods that has been developed by this year's laureates shows that this limit is not strictly enforced. Actually, it can be not only broken but superseded to any resolution. It's not applicable to any system. It means that we need to do some alterations to the system. First of all, we need to make them fluorescent. But if that is possible, the physical limit is much, much further down, which means we can study much, much smaller objects. And this turns microscopy into a chemical technique, while it used to be a biological technique.
So what new worlds can you see with this new microscope?
Well, I think the easiest way to look at it is to think back to when microscopes were first used. So the first images that were drawn from microscopes, that started microbiology. Now, what is happening now is that because we can see individual macromolecules moving about in a living cell, we can study chemistry at a single molecule level and in real life. And this is very, very important to chemistry because chemistry has traditionally been about studying a large number of molecules and the effect that they have. Here we can look at a single molecule as it is active in a chemical system. That means that rare events can be studied in a very different way. Reactions can be studied as they happen, not as the end result, but actually as they take place. It opens entirely new possibilities for chemistry and for biochemistry.
So this is like you previously could see an ant hill, and now you can follow every single ant.
You can look at the legs of the ants, and you can look at the damage done to the legs of the ant. Yes, and it's a fascinating subject, I think, because it is really a prize that goes into all the prize areas of the scientific Nobel Prizes. It has great potential in medicine. It is a prize which has a lot to do with physics, but it's also a prize that has a lot to do with chemistry. It's one of these prizes that eradicates the borders between the subjects.
But when you think about microscopes today, there are already microscopes with this super resolution, and it's different kinds of electron microscopes. So what is the difference? The
big difference is that a light microscope is much less damaging to what it studies. If you want to study a cell by electron microscopy, first of all you have to slice it very thinly because electrons only penetrate through a very small amount of matter. That means the cell is dead and you have to slice it, you have to fixate it with various kinds of stains to make the parts within the cell visible. This means that you do not have the dynamics, you cannot study real-life processes, and we have learned a lot from electron microscopy. It's a fantastic technique, but this takes us into the dynamic realm, and that is where real chemistry happens.
You don't want the dead ants, so to say, to study.
Dead ants are also interesting, and we learn a lot from dead ants, but live ants are better, and it's better for the ants too.
This prize is awarded actually for 2 different microscopes. Do they see different things as well?
It's really 2 different techniques, and they can be used on the same systems, but they also have their own limitations. You asked before about the fact that what are the new limitations? Well, for anything that works with fluorescence, which both methods do, you need to label the target of your study densely with fluorophores. And then you can see every individual fluorophore and thus the shape of the object that you're studying. Now, the the kind of fluorophores that you can use are different for these two studies. With the STED method that was developed by Stefan Hell, you need to quench the fluorescence using a very powerful laser that takes away most of the fluorescence. This can cause damage to living cells, simply photon damage, the same that you will encounter if you go to the beach without enough sun protection factor. Too much light is not good for you. So there are certainly limitations to both techniques, and they are slightly different, and therefore there is a complementarity here, but they also work very much on the same kinds of systems.
There is this common picture of inventors like artists, mostly poor and hungry and passionate. How do this year's Nobel Prize laureates fit into this picture?
Well, I think they fit very well. I think it fits particularly well when these inventors are doing something that is common knowledge is that it doesn't work. And so it's an uphill struggle until they succeed. This is quite common actually in science, and I don't think it's a bad sign. Science is rather protective of its paradigms, and it needs to be protective of its paradigms. Now, our laureates this year have changed those paradigms, and that is good. But at the same time that these people have worked, we have had hundreds of people who have worked on trying to change paradigms that stood up to the challenge. The paradigm stood up to the challenge. And it is important to defend these paradigms as well. These are what builds science. Every now and then we need to change them, but if we change everything at the same time, then the ground on which we stand starts rocking. And most of these things are actually true. Most of the paradigms have a very long lifetime because they describe nature in a correct fashion. In this case, the Abbe condition is still valid. These persons simply found a way around them. That's very good.
So you have to be quite a stubborn scientist.
You have to be stubborn, you have to have a very high opinion of your own ideas, and you have to have stamina. Those are very important character traits when you're battling with giants.
But did they give up? Do you know that?
There are stories from the autobiographies of both Erik Betzig and Stefan Hell that there were certainly periods of doubt. Erik Betzig left academia for some time because he considered that he was at a dead end, and Stefan Hell moved around a bit in order to find a place where he could conduct this work, and he needed to get a few theoretical studies in place to show that his ideas were valid. So yes, I think they were both on the verge of giving up, but they came back to this question because it was so interesting, it was so alluring, and the possibilities were so fascinating.
What were their reactions when they got the telephone call from Stockholm this morning?
Well, they seemed quite content. They were very happy. We managed only to get hold of Professor Hell and Professor Betzig. They are both in Germany at the moment. There is a meeting in Munich where Professor Erik Betzig is at the moment. Stefan Hell we caught at the Institute. They were delighted with the prize, and I think they agree with the committee that this is important work.
Thank you very much, Sven Lidin, for being here with us.
It's a pleasure. Thank you.